I am basically going to give an exposition uh, to the property D and its and how one gets examples of compact quantum metric spaces from property RD. Uh, so my own uh, uh, interest in it came via quantum groups. Uh, uh, I mean, it's actually possible to define, and I mean, not only possible but also useful to define and study property RD for discrete quantum groups. But for yeah, I mean, since it would be too technical, so I thought that I should convey the basic message. So the basic message in the in case of the groups and in the and in the quantum groups are the same. And yeah, so so throughout the talk, we will assume that gamma is a discrete countable group. So and C gamma is the associated uh, group ring. So yeah, I mean, let me change the color. Yeah. So so thus C gamma is equal to the set of all A gamma lambda gamma. Gamma belongs to uh, F, where F is a finite set. So F finite set. So lambda gammas, well, of course, you can also view them as functions on the group, but for the moment, just view lambda gammas as symbols. So so yeah, so the group ring is the collection of all possible finite linear combinations of these lambda gammas, and so it's a vector space, and the ring structure is given as follows. So it is actually the convolution uh, product. So if you take two elements, lambda gamma 1 and lambda gamma 2, so you define that to be lambda gamma 1 gamma 2 and extend on linearly on C gamma. So uh, I also have a star structure, well, an involution star. So star C gamma to C gamma. This is of course anti-linear. A gamma lambda gamma star is equal to A gamma bar lambda gamma inverse. So gamma belongs to some finite set. Okay. So it's a star algebra. So this involution is compatible with the ring structure. So what I want to do is that I want to define the reduced group C star algebra associated to gamma. So uh, so let us look at the left regular representation. So let L2 gamma be be the set of all square integrable uh, functions on gamma. Uh, so uh, you can hear me all right, is it?
Yeah, it's fine.
Yeah. Okay. Okay. Yeah. So this is the now this is going to be an inf infinite sum gamma such that yeah, so gamma in gamma such that sum over mod is finite. So this is a Hilbert space, uh, and so I I have I know that the group ring C gamma is a ring. So what I will do is that I will define a representation of C gamma onto I mean into bounded linear operators on L2 gamma. So I will define phi uh, C gamma to be L2 gamma by by the formula phi of A gamma lambda gamma. So gamma belongs to F. And so if I apply it on this delta gamma prime, so delta gamma prime is a function on gamma. We're taking value 1 at gamma prime and 0 elsewhere. So this I define to be A gamma delta gamma gamma prime. So gamma in M. So it can be checked that okay. So this extends to bounded operator on L2 gamma. Now, right. So pi is uh, is a star homomorphism. In other words, a representation of the star algebra C gamma. Uh, and now I can define the reduced group sister algebra. So you define the reduced group sister algebra. So R stands for reduced to be the norm closure of C gamma uh, inside L2 gamma. So this is a subset of yeah. So this is the definition. Okay. So so this is called the reduced group sister algebra, and this is a known fact that so gamma abelian implies C star gamma is equal to C of gamma hat by the given Normack theorem. Okay. So in order to, so this is the group sister algebra. Now, in order to define the property RD for on discrete groups, uh, I will need the notion of the word length function. So, Okay. Okay. So uh, the setup is as follows. So gamma discrete group, and well, actually, I will need more. Discrete finitely generated group. Otherwise, there is a problem. So I fix a set of generators S closed under taking inverse. Okay, so I will call this set S, and yeah, so E does not belong to S. So for okay, so since my group is yeah finitely generated, so such a set exists, and I can just make it in inverse closed by adjoining the inverses. So as a result, if you take any element in the group G, then it can be written as a string in elements in a string of elements in S. Okay, so for gamma in gamma, so we find uh, so length of gamma is equal to minimum of m, such that G is equal to sorry, gamma is equal to product over gk, so k is equal to 1 to m, and gk belongs to S, and product gk is a reduced word. So just let me know if you have any questions. Uh, so basically, I can write any element of the group uh, as as an well. So I can write uh, gamma as G1, G2, Gk. I can also write. It's also possible to write gamma as G1 prime, G2 prime, Gn prime. So I look at all possible such combinations. Of course, so these have to be reduced words. So reduced means that for example, this string should not contain any term anything like G1 prime, G2 prime, G2 prime inverse Gn prime. So all these G1, G2, Gk should belong to S, and I look at the smallest number of smallest length needed to express gamma as a product of elements in S. Okay, so L is called the word length function on gamma associated with S. I will just give one example. So I okay. Uh, I yeah okay. I well,
There is a question, what is L of E? Is there anywhere written L of E also?
yeah yeah. So it is defined to be zero.
Okay, E is the identity element. Okay.
Yeah, it is defined to be zero. So that's why I yeah I didn't take e to be in S. So this function L, of course, depends on the choice of the uh, generating set. So this can be seen very easily. So example, so take gamma to be S3. Now, okay, so take S1 to be uh, 1, 2, and 2, 3. Okay, so 2, 3 is equal to 3. So of course, so length of 2, 3 is equal to 1. Now, however, if you take take another generating set, 1, 2, 1, 2, 3, this is also another generating set. I think if you want to make it inverse close, just add 1, 3, 2. So then length of 2, 3 here is actually uh, yeah, bigger than 1. Okay, so so some properties of the length function. So so L of gamma is equal to L gamma inverse. Okay, so suppose the gamma S as above, and the third is the analog of the triangle inequality, which says that plus length of 8. So this is for all gamma in gamma and for all gh in gamma. So if a function on gamma satisfies these two properties, it's called a length function. So the okay, so I mean the function has to be also positive, but it's of course satisfied in the case of the word length function. So in particular, the word length function is a length function on gamma. So okay, now regarding geometry, so it can be easily seen that the word length introduces a metric on the set gamma. So the word length induces a left invariant metric rho on gamma. So this is by the uh, formula d of xy is equal to L of x inverse y. So L is the word length function. And if you change the generating set, then you won't get the same metric, but the changed metric will be uh, 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 yeah. I mean, so those two, so that this metric space and the changed metric space will be quasi isometric. So right. So now I'm in a position to define a property RD. So RD stands for rapid decay. Uh, so here is the definition. So finitely generated group gamma equipped with uh, length function L is said to be of is said to have property RD if uh, for all x in C gamma, so the operator norm of x, so what does it mean? So it means that so you view x inside uh, uh, CR star gamma, which lies in B of L2 gamma. So that operator norm, uh, and this is this has to be lesser equal to C times sum over G 1 plus length G to the power 2s mod AG square whole power half for some C and S positive. I have not told you what these AGs are. So X belongs to C gamma. So so X is equal to sum over AG lambda G. Some fun set. So this is the definition. Clearly, the right hand side is something like a Sobolev norm, and
But it's not a unit combination.
which one?
AGs are not unit.
Yeah, I mean they are because those are so the lambda g's are a basis.
Oh, I see. Sorry.
So so the property RD says that if you take any element in the group ring, so then the operator norm is majorized by Sobolev norm with a certain index. Okay. Okay. So I have received objections about this name RD because there are theorems which say that groups with RD actually have substantial growth. So well, uh, this property RD was probably first coined by Kohn. The
Excuse me.
connection, yeah, sure.
Is C and S, do they depend on X?
No, no. So if you fix gamma and the length function on the length function on it, so then the C and X are fixed.
Okay.
Okay. Now, I would just like to uh, just remark where this term rapid decay comes from. So, it's a proposition. So, define the okay. So gamma as above. So define uh, HT to be the Tth subalgebra space. So so yeah. So some over Cj lambda g. Uh, okay. How do I put it? Yeah. I mean, uh, sorry. So define uh, Ag lambda g is equal to sum over 1 plus length g to the power 2t times this is t 2t times ag square whole power half. So complete it to get Hilbert spaces HT. Now let H infinity is equal to intersection HT, T positive, and so gamma has RD with respect to L. So if and only if uh, the embedding I, so H infinity to CR star gamma is continuous. So it means that so there exists some C and P such that norm of Ix so this is the operator norm is less or equal to C times norm X.
So I just want to ask,
So yeah,
why do you take L of G? I mean, in generally, like for when we define subalgebra spaces, we take the eigenvalues, right? So for
uh,
the operator with respect to whichever you are constructing these spaces. So
well, actually, I until now I have only seen the sublime spaces from bounded subsets of Rn,
yeah.
uh, but so so they're the Fourier transform appears. But what's your question?
So I'm saying that why this
Once
particular
again,
choice of length of G? I mean, just like that, and just out of curiosity, I'm asking. When you define this HT, is there some reason behind it? You put the weight 1 plus L of G, no?
yeah.
I mean,
So it's the uh okay, how do I put it? So the Laplace, well, I mean, it is uh, mm, So, well, so this is the natural subalgebra space associated with L. Now, if you want to bring in the Laplacian, so there is something uh, closely related. So, for example, okay, so I am going to come back to this
Oh,
once again.
yeah.
But no. But to answer your question, let me define this operator. So I'm going to well. So this is uh, going to be an unbounded operator. So sum over a gamma lambda gamma in L2 gamma, such that sum over mod a gamma square length uh, gamma square is finite. So on D, uh, so D is defined on domain D. It is unbounded, and it is basically defined by sorry. This is delta gamma because I am in the Hilbert space, not in the group ring. This is a gamma length gamma delta gamma. And since you are talking about the Laplacian, so Laplacian is just uh, so the proper analog of the Laplacian is actually the d square.
Mhm.
So you can see this so the square of the length is coming.
Yeah. Mhm.
But I mean there is a well actually it's a reason I'm claiming that the analog of the Laplacian is d square. Uh, but uh, okay, what basically one can show that uh, show the following that okay. So first observe that this CR star gamma L2 gamma and this tau. So this is a GNS triple. The Kekefat-Knox Sigal triple. Okay, so so what is tau? So tau it is given by uh, mm, just AE. So if you take the gamma to be Z, so this will actually go and so then CR star gamma is equal to C of S1. This actually gives you the and again yeah, this is lambda gamma. So whenever I write lambda gamma, I think of it as an element here. When I when I write delta gamma, I see it as an element of the Hilbert space. Of course, I mean they are kind of identified by the GNS construction, but but yeah. And now since it's a GNS triple, and then and I have this operator D. So so uh, I have the associated map. Uh, okay, this is L2 gamma to um, well, I mean, sorry. Uh, so basically, from this, I can perform this space of one form, A D commutator B. where AB belongs to the group ring. And then I have an analog of the Dirac differential, omega 0, which is actually equal to, yeah, uh, which is actually equal to C gamma to omega 1. So D of, yeah, so D of A is just D commutative A. It's a fact that this guy extends to a bounded operator, and then my Laplacian is D star D. So, and if you so this L and this D square, so they're actually almost the same. And so this is the Laplacian here, and your, yeah. So uh, you would have put the yeah. So the eigenvalues of the Laplacian. What is it? Uh, just a minute. Yeah. So as you can see, so the eigenvalues of the Laplacian are just length gamma square. So if you define the Sobolev norm according to your kind of definition, so you will get something like length gamma power 2t, and and what I am getting are actually the same. So what I am using is just 1 plus length gamma power
Mhm.
2t, which is the same thing
Yeah.
essentially. Yeah.
Just to remove
So
the singularity for the
yeah, yeah. Sorry, what?
because length of E is zero, so you don't want it to be zero or something. That
Yeah, yeah,
non-zero function.
yeah, yeah, yeah. And what? Okay, so basically, what follows is that, so 1 plus d square power inverse is compact. So just so this capital D, which I wrote, uh, this D.
Mhm.
So I am going to, yeah. So this is just a minute. Yeah. So this D, and so just compare this with, okay. So it's compact if uh, the cardinality of G such that length of G is equal to n is finite for all n. So I have this property. So you need to so, sort of compare this with the fact that the Laplacian on a compact manifold has compact resolvents. And this fact, so you can sort of compare it with the fact that the eigenspaces, yeah, so non-zero eigenspaces of the Laplacian are finite dimensional. So there is an underlying, yeah, geometric picture, and of course, so this triple, I am going to come back to it. So this will be our gadget with which we will get some metrics on the state space of the uh, reduced C-star algebra. So yeah, So, yeah, so until now, are there any other questions?
How is the norm on H infinity defined?
Oh, actually, it's a pressure space. So you have got all these norms coming from HT. So for each positive real number, you have a norm, and then on the intersection, you have the pressure norm. So a sequence in H infinity converges if it converges with respect to all the T norms. That's the uh, yeah.
All right, thank you very much.
No, I wonder why H infinity is not zero.
Uh, okay. Why is it not zero? Well, I mean, even if it's zero, then basically. mm, oh, okay. Sorry. Yeah. So all these finitely supported functions all belong there.
Uh-huh.
So
Yeah,
yeah, I mean this group ring
yeah, yeah, yeah.
uh, belongs there. Yeah. Okay. Okay. So let me just give a few. Mention a few examples. So groups of polynomial growth. Uh, so hyperbolic groups, word hyperbolic groups, and it is also okay. So RD is closed under free products. Uh, yeah, amalgamated products. Uh, some uh, semi-direct products. Yeah, and of course, except apart from these, there are several other examples, but yeah. mm, So this was the first part of the talk. So let me just yeah. So the second part is the okay. We will come back to RD, but after some time. So we all know. So suppose that XD is a compact metric space, and so from D, from this metric D, one can define a semi-norm on the space of continuous functions of X. So define semi-norm. So L C of X to R by L of F is equal to supremum X not equal to Y mod Fx minus Fy by Txy. Okay. Well, actually, this is RE union infinity. Uh, so L is finite on Lipschitz functions. Okay. Before this, so before I proceed further, I will need to just recall one definition about sister algebra. So okay, actually I should have done this before. So suppose A is a sister algebra. Now small a belonging to A is called positive if there exists B in A such that B star B is equal to A. So it's just the analog of positive functions, and uh, a linear functional phi A to C is called positive if phi of A is uh, is positive for all A positive. Okay. Finally, so a state on A is a positive linear functional such that uh, a linear functional phi such that phi of 1 is equal to 1. Well, I assume that A is unital because uh, we will be dealing with only those algebras. Okay, so so positive elements are just analogues of positive functions. Positive linear functionals are just positive measures, and the states correspond to probability measures. So, okay, let me just give one example. So, A is equal to CR star gamma, then um, okay, so tau A is equal to the inner product 1, 1. So, this is state. So, this is an element in CR star gamma. So, it's an operator, and 1 basically stands for the yeah, I mean the yeah, is a state. Okay, now uh, now recall that uh, Gelfand-Marmach theorem says that so any commutative sister algebra unital is isomorphic to C of x, where x is compact. Moreover, the extreme points of the state space of C of x. C of x is a sister algebra. So the state space of the C of x makes sense. Now this is basically homeomorphic to x. Okay. Okay. So I know that that So XD compact metric space, then have L CX to R. So this L is defined in terms of D. Uh, okay, but conversely, so the was there any question? Okay, no. So, but the thing is that the metric can also be recovered from L. So L induces a metric on S of C of X via so D. So S of C of X are the probability measures. So this is equal to supremum F. LF is less or equal to 1 mod mu F minus mu F. Okay. Moreover, if you restrict, okay, I should call this DL, metric DL. So the obvious question is that whether this metric coincides with D. Now, how do I make sense of that? Because I can make sense of it by restricting DL onto the extreme points. Restricting DL onto the extreme points, which is homeomorphic to the space X, recovers D. Okay. So yeah, my time is almost up, so I should sort of yeah, hurry. So
You can
in
take
the classical,
5 more minutes if you want. That's okay because we started also a little late, so it's fine.
okay, okay, okay. Thank you. So in the case of a compact metric space, starting from the metric, I have a seminorm, and conversely from the seminorm, I have a metric on the I get back the metric on the space. Now, given a sister algebra, of course, I mean that does not correspond to any space, but one can still talk of the state space. So here is the question. So A sister algebra. So does there exist a seminorm on A which induces the weak star topology on the state space of A? So induces mean the following. So if you have a seminorm L, then the induced metric may be called DL. So phi psi, this is equal to supremum over phi of A minus psi of A. Now set of A such that L of A is less or equal to 1. Of course, now I mean I don't have any uh, space on it, but this is a minimum requirement. So does this does this have a metric? Now, we were talking about groups and length functions. So point the let me explain the connection. So, right. So gamma theorem. So suppose gamma is has polynomial growth uh, uh, mm, uh, hyperbolic or Zn, then uh, then define L CR star gamma. Sorry. So the C gamma to R positive. L of A is equal to the norm of the Dirac operator. By the way, so I should. So the first case was Ozawa-Riefel. No. Sorry. The first case was Christ-Riefel. Hyperbolic was Ozawa-Riefel. Well, I can actually forget Zn because it's because Zn is a polynomial growth. But a very interesting proof was given by Riefel himself. So then rho L induces the weak star topology on the state space of CS star gamma. Okay. Now the question is, what about RD? So question is, what about gamma with property RD? Well, okay. So suppose I have this estimate. This is C 1 plus length G power 2s mod AG square power half. So choose K bigger than S. So K a natural number bigger than S. Now define another seminorm LK. This is C gamma to R. So LK of A is equal to norm of, you take repeated commutators K times. So this is going to be a seminorm, and then the rho LK is yeah. So induces well, I mean, so yeah, so yeah, so it induces the weak star topology or state space of CS star. It would have been very nice if I could actually at least sketch the proof, but yeah. So this result is by Christensen Antonescu. and the same result can be proved for discrete quantum groups with property RD. But there you have to be careful with the choice of the sub, subalgebra norms. But it can be done. Yeah, I think I exceeded my time. Yeah, but yeah, so this is all I wanted to say.
Okay. Thank you for a very nice talk. Are there any questions? There is something written in the chat.
Sure. Uh, Actually, I I cannot. So should I stop screen share?
Yeah, you can stop. Yes.
So then I will be able to see the question.
Okay, you're not.
Okay.
So the question is that a group which does not have RD property, is there some example?
Yeah. There are lots of examples. So just a minute. So for uh, SLN3, for example, SLN3 and some amenable groups with exponential growth uh, and some intermediate growth groups. So I think these were by yeah yeah. So there are some examples.
Mhm.